Polynomial models in the real world means you're going to be working with data, actual data. And it's not just going to be making scatter plots and putting a line in there. It's going to be making scatter plots and putting in some sort of polynomial function to model the data. Because a lot of times the data that we find does not follow a line, but it does kind of follow a parabola or a cubic function or something like that. So we're going to learn how to make a polynomial model, not just a linear model. Read this. This is incredibly important. It's more my words than the book's words, and I'm kind of giving you an idea of what's coming in this section. It's incredibly important. So do I. All right, take the following data. So I'm giving you just a set of data, 5 data points, and plot them. Generate a linear, quadratic, and cubic regression, and then sketch the graphs and comment on the validity of each. So let's go ahead and do that. Let's make our scatter plot here. And we'll do that on the calculator. So go ahead and go to the spreadsheet on the calculator and enter that data in and then create the scatter plot. So here is my scatter plot. You can see that the data doesn't necessarily make a line, right? But if I put a line in here, I kind of think maybe it looks like that. The data doesn't really look like a parabola either, but if I put a parabola in here, it's probably going to look kind of like that. I can maybe make a cubic function, some sort of snake pattern that maybe matches up pretty well. I don't know. Okay? And that's what we're being asked to do in these 3 things. So I'm going to go ahead and get rid of this window, and I'm going to put the little sketch on here of each of these 3 things. All right, now I'm going to go ahead and put a linear regression on this scatter plot here. So remember to do that: menu, analyze, and then regression, and then linear. Show linear. And there's my line. So we'll sketch that line on the linear scatter plot that we made on the notes. I'm also going to put a quadratic on there. So same thing: menu, analyze, regression, but this time quadratic. And we've used that one before. So now I have also a parabola. The equation itself right now doesn't matter. It's just the shape of the graph that I care about. We'll deal with the equations later on. We also want a cubic. So I'll do this again one more time. Analyze, regression, this time cubic. And hit enter. And if you look at the cubic one, you can see that that cubic actually goes through all of the points. So now I'm going to sketch these onto my notes so that I can kind of see what it is that I'm talking about here. So my linear one, my graph is going to disappear, but my linear one looks like this. My quadratic one kind of looked like that. And my cubic one, interestingly, went exactly through all of my points. Of course, my sketch is terrible, but it goes through all the points. Exactly. So it says take the following data and enter it into, okay, generate a linear quad, okay, we did that. Sketch the graphs and comment on the validity of each. So we sketched the graphs. Now we need to talk about how valid these graphs are. Well, the only one that went through every single point was the cubic one. This one came closer to all the points, but didn't touch any of the points, and that's okay. It's a scatter plot. This line also came close to all the points, but didn't really touch any of the points. Do we see sort of a pattern here in these numbers? Does it appear that they're always increasing? No, because we went pretty low there, and then we came back up, and then we were increasing. Okay? Does the line show that? Would my equation for a line show that decrease and then increase again? No. Would the graph for the parabola show that? Decrease and then increase again? Yeah, it does. It shows the decrease and then it comes back up here. Does the cubic function show that decrease and then increase again? Yes. But what the cubic function also does here is it goes back down for forever. Based on what I see in these 3 data points right here, does it look like these numbers are going to start going back down? No. I have no indication that says that these numbers are going to turn back around and go back down. I have no idea what this data set even represents. Okay? So because of that, this region right here, I'm a little sketched out about. I don't know what to make of this. The cubic function made this happen. But without more data here, I don't know for sure what's going to happen. I don't know if this is actually going to go down. It might continue to rise, and maybe this actually was sort of a line coming through here, and it should continue to rise. I have no idea. Okay? So just because the cubic function goes through all of those data points that we have perfectly, that doesn't mean that that is the perfect function, because we don't know the situation. Once we know what the situation is, then yeah, maybe we can comment on whether or not these numbers are supposed to come back down. Okay? That's the idea that's going on in this section. So we have to think a little bit more than just, okay, this one goes through all the points, so it must be great. It may not be. It may be terrible. So if you notice on that last problem, we had how many data points? There were 5. There's this key concept right here, the n plus 1 point principle. If you remember back to a couple chapters ago when we learned about making a parabola fit, how many parabolas go through exactly 3 points? 1 parabola. So in other words, in order to make a parabola, how many points do I have to have? 3. In order to make a line, how many points do I have to have? 2. What is the degree of a linear function? A linear function is a first degree function, and I need 2 points to draw a line. A quadratic function, a second degree function, graphs a parabola. How many points did I need there? 3. So a second degree function needs 3 points. For a cubic function, how many points do I need? I need 4. And that's what the n plus 1 point principle is. If I have n plus 1 points, so if I have 5 points, then I'd have 4 plus 1 points. Okay? What that means is there's a unique polynomial of degree at most 4 that fits the points perfectly. So if I give you 6 data points, then I could create a 5th degree polynomial that goes through all of those data points perfectly, as long as all those data points pass the vertical line test. If I give you 3 points, then you can give me a 2nd degree polynomial that passes through all 3 of those points perfectly. If I give you 2 points, you can give me a 1st degree polynomial. Okay? If I give you 99 points, you can give me a 98th degree polynomial that passes through all of those points perfectly. That's what the n plus 1 point principle says. Well, it's an even degree polynomial, so it looks like a U with a bunch of stuff going on in between. There's your graph. Okay? All right, so we already know that 2 unique points form exactly 1 line. We learned that 3 unique non-vertical points form exactly 1 parabola. And the n plus 1 point principle says we can extend that and say that exactly 1 polynomial fits all of the points perfectly if that polynomial is 1 degree less than the number of points that you're given. That's this point principle here. And we're going to use that to create models. And then we're going to talk about how valid those models are. So, for example, what polynomial function has a graph that passes through the 4 given points exactly? What degree polynomial am I going to need? A 3rd degree polynomial. No, we're not just going to graph it because we don't have a function to graph. A 3rd degree polynomial has the form y equals ax to the 3rd plus bx squared plus cx plus d. In chapter 4, when we had just 3 points and we were making a parabola, we took all 3 of those points, the x and the y, the x and the y, the x and the y, and we substituted them into our equation. We came up with a system of 3 equations, and then we plugged them into a matrix, row reduced it, and got the coefficients a, b, and c. We are doing exactly the same thing here, but now it's going to be a, b, c, and d. 4 variables, 4 equations, a 4 by 5 matrix. Yes, it's not that bad. So it says first, what will the degree polynomial be? We said it's a third degree polynomial because we have 4 points. 4 minus 1 is the degree. 4 minus 1 is 3. Write the polynomial with unknown coefficients. That's this right here. Y equals ax to the third plus bx squared plus cx plus d. That's the form that we're looking for. Now, next, substitute each point in for x and y and simplify. So for my first equation, I'll use my first ordered pair. 0, negative 3. Y is what? It goes x comma y. So y is negative 3 equals, now we have a times 0 to the third plus b times 0 squared plus c times 0 plus d. Which means that this equation turns into negative 3 equals, basically, 0a plus 0b plus 0c plus d, 1d. You don't have to write the zeros in, but you're going to enter them into a matrix, and what I'm doing right now is creating all the columns for a matrix. So now the second ordered pair, 1, negative 1. That means negative 1 goes in for y, and 1 goes in for x. So I have 1 to the third, which is just 1a, plus 1b, plus 1c, plus 1d. For my third equation, I have this ordered pair, 2 comma 5. So 5 goes in for y equals, I'm plugging 2 in for x each time. So 2 to the third is 8a plus 2 squared is 4b plus 2c plus 1d. And my last point, negative 7 equals negative 1 to the third, which is negative 1a, negative 1 squared, which is 1b, so plus 1b, negative 1 times c, which is negative 1c plus 1d. I wrote it out like that. I didn't need that top one. I wrote it out like that so that you could see all the coefficients for the matrix that we're about to use. Now remember, the answer column is supposed to go where? All the way on the right side. So my matrix is going to be 0, 0, 0, 1. And then my answer, negative 3. Then 1, 1, 1, 1, negative 1. Then 8, 4, 2, 1, 5. And finally, negative 1, 1, negative 1, 1, negative 7. What are we going to do? RREF. And we'll get an answer matrix that looks like this. 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, and then a bunch of answers. What are my answers? One, negative 1, 2, and negative 3. So those are the coefficients A, B, C, and D for my polynomial right here. So now I can write my polynomial. Y equals 1 x to the third minus 1 x squared plus 2x minus 3. There's your polynomial. All right, let's try this one. It says, what polynomial function has a graph that passes through the 4 given points exactly? Now, what degree polynomial are we talking about here? This is a third degree polynomial because we have 4 points. So it's a third degree. Talk me through it. I do want to write it down. My function is y equals Okay, so we have ax to the third plus bx squared plus cx plus d. Writing that down helps you remember what's going to go into each of those positions as you write this, okay? So let's start writing the equations. 1 equals a times negative 2 to the third. What is negative 2 to the third? Negative 8. So I'm not going to write a times negative 2 to the third. I'm going to write negative 8a. That saves me time and space. Negative 2 to the third. Okay, so now we have the next term, negative 2 squared. So plus 4b. Next term. Minus 2c. Just plus d. There's no x to substitute in for there. Next one. Good. Next one. It's 2 to the third, 8a. Good. And the last one.
How come D never changes?
Because there's no variable on D. We're substituting in for x and y. There's no x here to substitute a number in for. On this one there is, on this one there is, on this one there is. It's just D all the time. 36 equals 27a. Okay, so those are your 4 equations. Now what? Write the matrix. What is the matrix going to be? Okay, next one. Good. Next one. Okay. Okay, now what? And do what to it? REF. So we're looking for an answer. It's going to look like this. Okay, so we got fractions. Does that mean everything is bad? No. You just write it down. The equation will be what? Y equals 5/3 x to the third. Good. That's it. The x squared term had a coefficient of 0, so it disappeared. This is the polynomial right here.